The objective is autonomous aerial inspection. We are building a system where a drone navigates critical data center infrastructure, evaluates real-time thermal conditions, and executes operational decisions without human intervention. To get there, we start with ThermalSight. This is a proof-of-concept digital twin designed to test physical robotics and AI perception in a strictly controlled, simulated environment. The engineering plan was straightforward. I intended to run the physics simulation, the drone models, and the AI brain together inside a single, unified Linux workspace. The architecture broke completely before I could write a single line of control code. Theoretical infrastructure plans rarely survive first contact with the actual compute environment. The breaking point was Isaac Sim's RTX graphics pipeline. It fails silently when forced inside a WSL2 container. WSL2 is the Windows subsystem for Linux, a compatibility layer that lets developers run a Linux environment directly on a Windows host. While the subsystem handles raw GPU compute tasks, the advanced rendering engine cannot display a viewport. The terminal simply loops a missing NVIDIA kernel error. An NVIDIA engineer confirmed this limitation. It is a hard hardware-to-OS boundary that prevents the RTX renderer from communicating through the virtualized Linux kernel. Without that renderer, there is no virtual warehouse. There is no physical twin, no synthetic sensor data to feed the cameras, and no environment to train the AI. If the operating system cannot render the physics, the intelligence layer has nothing to observe. The system dies at the hardware level. Recovering from this required abandoning the single system approach entirely. I rebuilt the project from scratch using a split system architecture. In this setup, the simulation runs natively on Windows. This grants the Isaac Sim engine full, unrestricted access to the GPU rendering pipeline. The cognitive controller remains isolated in the Linux environment. This node runs the Python stack and ROS2, the middleware suite used for building and managing robot applications. This hardware division mirrors how production digital twins are deployed. Real-world enterprise simulations and their corresponding control software run on distributed, separate machines. The WSL2 rendering failure forced a design choice that turned the project into a credible distributed network. Splitting the system created a new engineering problem. The Windows simulation and the Linux AI now had to communicate across an operating system boundary. The connective tissue for this is DDS, the Data Distribution Service Protocol used to publish and subscribe to real-time data across a network. Out of the box, this bridge is blind. The simulation on Windows and the controller on Linux cannot see each other.
The culprit is the Windows firewall. Its default security rules block the multicast discovery ports required for DDS to function. Fixing this requires manual intervention. I explicitly wrote PowerShell rules to open UDP ports 7400 through 7500, plus port 111811, allowing the telemetry traffic to pass. Simulation software often abstracts networking away, but building an operational system requires explicit manual network handshakes at the protocol level. Even with the firewall open, the simulator remains silent. It publishes zero data to the network. The missing step is OmniGraph, NVIDIA's visual scripting engine.
You must build a graph to explicitly command the publication of ROS2 topics. To test the bridge, I wired a playback tick node to a simulation time node, forcing the simulator to push a clock signal across the network. Neither the firewall blocks nor the manual OmniGraph routing are prominently documented in standard tutorials. In a distributed digital twin, data flow is never automatic. You must aggressively architect and route it at the node level. By the end of the first sprint, the split architecture was staged and fully operational. This image shows the physical twin, an Iris drone model loaded successfully into a virtual warehouse environment running natively on Windows. It passes the initial physics check. The drone drops under simulated gravity, resting firmly on the floor without clipping the geometry. In the isolated Linux terminal, querying the active topics reveals the clock data flowing in from the Windows machine. Proving the data pathway is the hardest part of standing up a distributed system. With the network bridge secured, the drone is ready for a brain. We transition from the physical twin to the cognitive controller by building an OODA loop inside the Linux environment. OODA stands for Observe, Orient, Decide, and Act, a cycle for autonomous decision-making. The first cognitive layer in this loop is a PID controller, a mathematical algorithm that calculates and corrects physical errors. This runs 50 times a second to maintain immediate flight stability. This diagram shows the second layer, an MPC optimizer, an algorithm using a mathematical model to optimize future actions. The PID controller reacts to immediate physical drift. The MPC optimizer looks ahead, predicting thermal states to calculate the most efficient enterprise cooling response. This diagram maps these horizons onto the architecture. The top sequence tracks the continuous telemetry cycle between the simulation and control node. If the drone detects a thermal anomaly exceeding 85 degrees, the system transitions into an investigation phase, issuing commands to increase liquid cooling. An operational digital twin calculates the optimal future state and issues the physical commands to achieve it. It converts a passive alert into a closed loop of sensing, optimization, and action. This drone testbed is the foundation for a much larger enterprise vision, HelioViews.
ThermalSight serves as phase 0 of the platform, the proving ground where we master sensor calibration, failure analysis, and alert triage under controlled conditions. HelioViews scales this capability by grounding the telemetry in a planetary scale context. It uses cesium to map simulated sensor data onto precise 3D geospatial environments. The final operational layer integrates Palantir AIP, connecting the AI models to enterprise data. This turns raw sensor anomalies into auditable actions across critical infrastructure. The technical friction of this project, the firewall blocks, the OS boundaries, and the manual graph wiring, illustrates why end-to-end infrastructure twins are rare. HelioViews is built on this specific connective tissue. It functions as the operational surface, where simulation, geospatial context, and AI reasoning converge into a single data pipeline. Rebuilding from architectural failures at the microscale is the prerequisite. It is the only way to earn the right to govern infrastructure at the macroscale.